So, good morning. Welcome to Krishna's classroom. We shall record the concluding part of our lectures on determinants. This is the ninth part. In fact, I was thinking of winding up with the last episode, but I thought that I have to make some remarks about the geometric interpretation. Maybe worth it. That's the reason. Yeah. So the emphasis in this talk will be on the geometric interpretation of a determinant. So we shall just recall, we are working on Rn, as I have said many times, that Rn can be replaced by any n-dimensional vector space over some field F. So here we are looking at Rn over R. Now we have seen that the alternating n-linear forms on Rn forms an n-dimensional vector space of dimension so one-dimensional vector space. That's a fascinating picture. What you call an alternating n-linear form is a map from R, which is linear in every argument. The arguments are elements in Rn. When others are held fixed, so that's an n-linear form. Now, an alternating n-linear form has the further property that if you interchange any two distinct arguments, then the sign will change. Okay. Or we can put it this way, and the consequence of this is that f of this is equal to what is called the signum. Sigma is a permutation on n symbols. F of the sign of sigma, it could be either +1 or -1. Okay, so this is what we. So this is the property of an alternating n-linear form. So F is Now we shall introduce some notations which we had been using and which are useful also for our purpose. So let us denote by E sigma 1, E sigma 2, here sigma is a permutation. So okay, E sigma n. So this is something like E1, E2, E3, En. That's the identity permutation. So that is when sigma 1 equal to 1, sigma 2 equal to 2, etc. sigma n equal to n. Otherwise, sigma is a permutation, then one could get mapped to any element and so on. So depending on what that permutation is. And we have defined, of course, sigma belongs to En, a permutation of then n elements 1, 2, 3, etc. n. Or you can even say n symbols. Now we define all these are the notations that we have introduced earlier. This is a symbol actually. Where EI tilde equal to delta ij, and we have and we write E sigma tilde acting over E tau, where sigma and tau are two permutations. This is defined as E sigma 1 acting over this is the product E acting over E tau. Now therefore what you have is this, that is E sigma we shall write it as delta sigma tau, by which you mean, and delta equal to 1 whenever sigma equal to tau, and sigma naught. That's our notation. Yeah. So if F is an alternating n linear form, F can be written as a linear combination of E sigmas. Okay. And eventually what one gets is the following. That is, so we will designate the following. Let lambda denote find box. Let lambda be defined by summation over sigma sine of sigma times E. So let this is a notation where sigma of course belongs to Pm. That is, it's a permutation of n symbols. Okay. Now you can easily verify that lambda is alternating in linear form all this we have written, and it forms a basis for the vector space of alternating what I mean to say is lambda is not equal to 0. Okay. Not only that, for instance, lambda acting over E sigma is equal to sine of sigma E sigma tilde into E sigma. Therefore, that's equal to plus 1 if sigma is an even permutation, minus 1 if it's an odd permutation. So, it is non-zero, and this is a one-dimensional vector space. Therefore, this every n-linear alternating n-linear form can be expressed as a scalar multiple of lambda. Alternating multiple of lambda. Precisely, if f is a alternating n-linear form, then f is equal to f of e pi where E pi is identity permutation, therefore E pi is E1 En. That is, pi is the identity permutation. Okay. So this is the background that information that we make use of. These are the notations that we have already explored and introduced earlier, and this is precisely the basis vector that of the space of alternating and linear forms. And every element of that can be expressed as a linear, as a scalar multiple of scalar. Now this is precisely what we have proved so far in the last lecture. Now we shall look at what this means in the case of n equal to, and then we analyze n equal to 2, n equal to 3, which will give you some insight into the geometry of the determinant, and then we will just make some interpretation of the general case. So let us take the case n equal to. Then what you have is, see, the permutations of two symbols are, there are two permutations. One pi is 1, 2 getting mapped to 1, 2. This is identity. And sigma, let me just designate it by sigma to be equal to 1, 2, 2, 1. These are the two distinct permutations that you have. Therefore, in this case, lambda is equal to E pi tilde minus, let me just convenience or more expressively, we shall write E pi, which is equal to E1, E2, which is equal to, write it as E1. Similarly, E sigma equal to E2, E1, which you write as E21. And therefore, we write E pi tilde is written as what is called E1, 2 tilde. E sigma tilde you write as E21. The property is that E12 tilde acting over E12 will give you 1. On all other things, it is 0. E sigma tilde acting over E21 will give you 1. All others are 0. So these are non-zero entities. Okay. Therefore, we have now lambda written as And you see that this sigma is 1, 2 going over to 2, 1. 1 going to 2, 2 going to 1 is an odd permutation. Therefore, you have a minus sign. Okay. So, this is what you get. Okay. Now, let us compute the following. What it does on a pair of vectors. So, let now x can be written as x1 e1 e2. Y can be uniquely written as y1 e1, where x1, x2, y1, y2 are real numbers in this case. Okay. Now let us compute. So these are, so xy now let us compute lambda of x. Let me now compute lambda of xy. This is in fact equal to lambda of if you use two linear, by which you mean it is linear in the first argument when the other is fixed, and it is linear in the second argument when it is held, the first argument is held fixed. What we have is this is equal to lambda xy equal to x1 y1 x2 y1 that is essentially x1 y1 lambda of E21 x2 y2 of. Now it is easily seen that lambda is of course given by therefore you working with this you get lambda xy equal to, see, lambda E11 is 0 because it is E12 tilde acting over E11 minus E21 tilde acting over E11. Both the cases they are 0. So this is 0. So what is left is this x1 y2 and this you can easily see that this is equal to E12 tilde E12 is 1, E21 tilde E12 is 0, therefore this is equal to x1 y2 plus minus sign of course E21 tilde because you have Eij delta ik this is the reason. So what is it? This is equal to 1. This is also equal to 1. Therefore this is equal to x2y. And what is that? That is nothing but determinant of okay. So the action of lambda on xy produces the determinant of x1 y1 x1 x2 y1 y. Okay, that is x1 y2 minus x2 y. So this is what you end up with. Okay, but what is it? Let us explore this now. Now let me work on the geometric picture of the whole thing. So what one does is the following. Now suppose you take in R2, suppose x is a vector, y is the vector, not necessarily in the first quadrant. I am just for convenience just drawing it in first quadrant. Okay. Now these points are x1, x2. This point is y1, y2. That is why you have it is x1 e1 plus x2 e2, y1 e1 plus y2 e2, where e1 and e2 are the unit vectors which form a basis for R. Therefore, now let us take the parallelogram determined by these two vectors as sides. So let me complete the parallelogram. Now what is the area of this parallelogram? The area of this parallelogram is, see, the area of this parallelogram is given by x1 y2 minus x2 y1 is the area of the parallelogram. Determined by x and now, okay, or I can write it as that lambda of xy computes the area of the parallelogram determined by the vectors x and y in R2 as adjacent sides. So I can write this as this. So this area is essentially lambda of okay. Now let me also have a different look at this whole thing. Now we define, let T belong to LR2 determined by TE1 equal to x, TE2 equal to. That means, if you prescribe T on a basis in R2 and then extend it to all the vectors linearly, you get a linear transformation. And this is the unique linear transformation that we have described. X and Y, in fact, defines the particular linear transformation. Now, T is a linear transformation from R2 to R2. So, what is the picture that you have? The picture that you have is this. This is E1, this is E2, and then consider this box. These are the two vectors which are linearly independent and forms a basis for R. Now you see that E1 gets mapped to X. E2 get mapped to Y. Okay. Now what happens is that look at the area of the square determined by E1 and E2. Now this is equal to 1. This is the unit area. Look at the area of the parallelogram determined by X and Y. This we have just now calculated, and that is equal to lambda of X. This is what we have calculated here. Okay. So what happens is that under this linear transformation T, what you obtain is that the unit area is mapped onto the area lambda xy. So we have already seen this. We will recall what we did in the context of a linear transformation. Now you see that lambda xy is equal to lambda TE1 TE2. And this we have seen that lambda is an alternating two linear form. Therefore, this is equal to determinant of T into lambda of E1 E2. So what happens is this is actually the area of the square determined by E1 and E2. The multiplying factor is what you call determinant of T, and this is essentially equal to x1 y2 minus x2 y1 multiplying which is equal to okay. So this multiplying factor or the scaling factor of this area is given by lambda xy. Okay. So lambda xy actually corresponds to the scaling factor that goes how this unit square is getting mapped in under the map TE1 equal to x, TE2 equal to y. This is the interpretation of lambda xy, which is essentially the determinant of T. Okay. So that's the interpretation of the determinant. Okay. This is interesting. Now let us take up the case n equal to 3 is a bit more sophisticated, but it's very interesting. So for n equal to 3, now you see that there are 6 permutations to be, because we are working on 3 symbols and there are 6 permutations. So let us write down sigma 1 to be the permutation 1, 2, 3, 2, 1, 2. Sigma 2 is the permutation 1, 2, 3 going over to 1. So these are notations. Sigma 3 we designate 1, 2, 3 going to 2, 1, 3. Sigma 3 or sigma 4 we designate as the permutation 1, 2, 3 going over to 2, 3, 1. Sigma 4 we write as or sigma 5 is the permutation 1, 2, 3 going over to 3, 1, 2. Sigma 6 is the permutation 1, 2, 3 going over to 3. Now sigma 1 is pi. And its sign is plus. Okay. Now we will interpret each one of these and look at the sign of each of these permutations. Okay. Sigma 2 equal to minus 1. This is because sigma 2 equal to can be written as the transposition 2, 3. Transposition 2, 3 means 1 goes to 1, 2 goes to 3, 3 goes to 1. And that is this permutation, sigma 2. Now, sigma 3 equal to, I will write this as, it can be written as the transposition 1, 2. That means 1 goes to 2, 2 goes to 1, 1 goes to 2, 2 goes to 1 and 3 goes to 3. Again, sign of sigma 3 is equal to minus 1. Okay. So, we look at sigma 4 equal to the product of transpositions 1, 2, 2. Just you verify. That is 1 goes to 2 and of course 2 goes to 3, 3 goes to 2 and here 1 goes to 2, 2 goes to 1 and you take the product. First act with this and then act with this, so you get this permutation. So this means sign of sigma 4 equal to plus. Now we have sigma 5 it's an even product of transpositions. That is why it is the sign is plus 1. And sigma 5 is again a product of two transpositions, namely 1, 3, 2. Therefore, sign of equal to plus 1. And now come to the next one, namely sigma 6. These are the 6 permutations that will go into the representation of lambda. Sigma 6 is actually the transposition 1 goes to 3, 3 goes to, or the permutation 1 goes to 3, 3 goes to 1 and 2 goes to 2. Therefore, sign of minus 1. So these are the permutations that you have and their signs. Therefore, using this, one can write lambda is written as, let me write this in this way. This is 1, 2, 3. E sigma 1 tilde minus E minus E sigma 3 tilde plus E sigma 4 tilde plus minus E. These are the 6 permutations that you encounter, and they are the signs of that. You see, what happens is, see, if you have take the class of permutations of n symbols, what happens is it can be classified into even permutations and odd permutations, depending on the number of factors that appear in their representations in terms of the product of transpositions. Transposition means interchange of any pair of indices. And what is important is that the representation of a permutation as a product of transpositions is not unique. However, if one representation has even number of products of transpositions, then every other representation has only even number of transpositions. Similarly, if one particular representation has odd number of factors, then every other representation also has only odd number of factors. So based on this, we classify the permutations into odd permutations and even permutations. And sigma 1 is an even permutation, sigma 2 is an odd permutation, sigma 3 is an odd permutation, sigma 4 is an even permutation, sigma 5 is an even permutation, sigma 6 is an odd permutation. Therefore, you have the corresponding signs coming. Therefore, this is the detailed expression of this. Now, let me just better visibility. We introduce the following notation. Let me write E sigma 1 that is 1, 2, 3 going to 1, 2. E sigma 2 I write as E 1, 3, that is 1, 2, 3 going to 1, 3. I have written. Similarly, E sigma 3 tilde equal to E 2, 1, 3. E sigma 4 E 2, 3, 1. That is 1 goes to 2, 2 goes to 3, 3 goes to 4. This is the notation. These are all notations. E it's all sorry. So this I write as E sigma 6 is essentially E 3, 2. So these are the new notations that we have introduced. And accordingly, we can rewrite lambda in the following. Now that is easier for further conversions. Therefore, lambda is equal to E1, 2, 3 minus E1, 3, 2 minus E plus E minus E3, 2, 1. So these are the permutations. So this is the expression in terms of Eijk. Okay, right? And we know the properties of this Eijk. Tilde acting over equal to delta IL delta JM delta. So if LMN is equal to IJK, then see you get 1, otherwise you don't get 0. So that's the interpretation. Now we shall use this to compute lambda of where XYZ so X is in R3, Y is in R3, Z is in R3. So let X be then uniquely determined as X1 E1, X2 E2 plus X3 E2. Y be written as uniquely as Y1 E1, Y2 E2, because you can find scalars. So that means with respect to the coordinate system E1, E2, E3, this is X is represented by X1, X2, X3, Y is represented by Y1, Y2, Y3. Now I take Z to be represented by Z1, Z2, Z3. We write that is the unique representation. That means the triple Z1, Z2, Z3 represents Z with respect to the ordered basis E1, E2. That's the meaning of that. Now compute this. Compute lambda. I am not going to do the detailed calculation. What I have to use is that lambda is 3 linear. See, lambda is okay. That means lambda is linear in each one of these arguments when the others are two others are held fixed. And using that, we write this as lambda of x1 e1 plus x2 comma then z1 e1 z3 e3. Now this, if you expand using the property that lambda is 3 linear, that means lambda is linear each of the argument when others are held fixed. If you perform this operation, this is what you have, and lambda is given by this one. In fact, so this is the expression for lambda. So we shall use this. This is your lambda. Now let us work on this. Now you see that E1, E2, E3 is what is called E1, 2, 3. Okay. You see E1, E1, E1 will be E1, 1, 1. And the action of any one of these on E1, 1, 1 is going to be 0. So use such facts about this, then this expands to x1, y2, z3 minus x1, y3, z2 minus x2, y1, z3 minus, or rather plus x3, y1, z2, x2, y3, z1, then you have plus this is what it turns out to be. All other terms will become 0. And this needs little bit of computation. It's quite easy to see. You see that when you work with E tilde 1, 2, 3, you are using E1, E2, E3 will give you the 1. All others will give you 0. Therefore, the coefficients are x1, y2, z3. Similarly, you calculate with each one of these. Okay, right. Now, here you are using this property, namely that I have said somewhere. Yeah, Eijk tilde acting over ELM n is given by delta IL, delta JM, delta K. We use this property to expand the whole thing. So this can be written in this following form: x1 into minus x2 into y1 z3 minus now this can be written as the determinant x1, y1, you are expanding on the first column. Okay? Therefore, this is equal. So what you have is that lambda xyz. So this is your where did we start? We started with this. But what is this? This is essentially in our vector analysis. This is x dot y cross the triple product that. Okay, and you see that this is an alternating n linear form. Okay, but what is it? This is this, and this is what in R3. If you take three vectors, one x, another is y, another is z. Let us take three vectors x, y, z, and then let us complete the parallelepiped. This is it. Then you have this is the parallelepiped created by the three vectors x, y, z. Okay, and you see that x dot y cross z essentially corresponds to what is called the volume of this particular parallelepiped. Okay, so the volume is given by equal to which is equal to lambda of so lambda has the role of computing the volume enclosed by the three vectors x, y, z. Now let us look at a few scenarios of special cases. Suppose all the three columns are linearly independent. If the three columns are linearly independent, then this is different from 0. Then there is a very definite positive or negative, depending on x, y, z corresponds to a positive volume, say. Then you have, if I interchange two columns, which corresponds to interchanging x with y, what happens? This determinant will change sign, and that corresponds to a negative volume, and with a minus sign. Okay, if you take this one with a positive sign, then the other one is going to be the negative sign. Now, if you make two interchanges of the columns, then what happens is two interchanges means x is interchanged with y, z is interchanged with xa. So if there are two interchanges happening, then you get again positive volume. So what you have is that, these are the normal properties of x dot y cross z. You interchange x with y, then the sign will change. Okay, these are the facts that we look at. So this is the property of this alternating form, alternating three linear form. So that's what you have, and the determinant actually represents what is called a lambda of x, y, z, where x corresponds to the vector x1, x2, x3, y corresponds to the vector y1, y2, y3, z corresponds to z1, z2, z3. Now, when do you get 0? Suppose 2 or one column is the linear combination of the other two sets. What does it mean? It means this vector, suppose y1, y2, y3 is a linear combination of x1, x2, x3 and z1, z2, z3. Then what happens? The vector y lies in the plane determined by x and z. Okay. In that case, what happens? The parallelepiped will collapse to a parallelogram. Okay. So if you have both the columns as scalar multiples of this, then you are going to have it collapsing into a line. Okay. So the whole thing will collapse into a line. In that case, you get 0 volume. Okay. So these are all there when you say lambda is a alternating n linear form, and this is the basic alternating n linear form which corresponds to the other things. And now further we have a similar analysis for the following. Suppose we now define T, a linear transformation T on R3 by this x, y, z determines a linear transformation T by prescribing T1 equal to x, T2 equal to y, T3 equal to z. Then what you have is this lambda of and we have already seen that this corresponds to determinant of T multiplied by and lambda of E1, E2, E3 this is equal to 1. Therefore, that is another interpretation, another way of looking at it, which corresponds to saying that, you see, when you have in R3, you take E1, E2, this is E1, E2, E3, then you have the basic volume, the basic cube that you have. Okay, this is the cube made by the vectors E1, E2, E3, which has volume equal to 1 unit. And then what happens is you are looking at the transformation T of E1, T of E2, T of E3. That is given by x, y, z. And look at the cube that you, or look at the parallelepiped that is determined by these three vectors. And then you see that this volume is now scaled by what is called a lambda xy z. So lambda xy z, or the determinant of T, essentially gives you the scaling factor. When you go from the standard cube E1, E2, E3 to X, Y, Z, the parallelepiped X, Y, Z. So that is the interpretation there. Okay, fine. Well, that completes the picture in R2 and R3. Now let us go to the case of N, which we have already discussed in detail. Now we need only interpret it. Okay. So let me take out this. We now go to the general case N and what we have to do. Take up the case n-dimensional case. What happens? So we are working on R. Okay. Now you see that the basis for the alternating and linear forms is given by the particular alternating and linear form, lambda defined by, we have seen this elaborately, summation over sigma belonging to Pn, that is permutation of n symbols, sine of sigma multiplied by E sigma, where sigma is a typical permutation of the class Pn. Now let us take vectors x1, x2, xn, n vectors, xi belongs to each xi belongs to Rn for I equal to 1 to. Now you see that each xi can be written as a unique representation in terms of E1, E2, etc., En. And this is given by x 1i E1, x 2i E2, for I equal to, these are the n vectors, where xij's are uniquely determined because E1, E2, etc., En forms a basis for R. Now let us compute this. So this I write as, so let me compute this, lambda of let me calculate this. This is equal to lambda of x11 E1 plus x Q1 Q2 here. And now I use the n linearity of lambda, using the n linearity of and E sigma this property, we get, okay, we see that this is equal to lambda, this is equal to summation over sigma sine of sigma x sigma 1 1 x sigma 2 2 into P theta sigma E sigma, and this is equal to because E sigma tilde E sigma is equal to 1. Okay, and this is nothing but the determinant of x1, x2, etc. Okay, and which is essentially in the general form we can write the following. We have this given by determinant of x11 this is the determinant. Okay, and if T belonging to LR is determined by xn. Then you see that lambda of, okay, then you see that the lambda of x1, x2, etc. xn is essentially lambda of n. This we have already seen that this is equal to determinant of t multiplied by lambda of en, which is equal to t, because lambda of e1, e2, en is actually lambda of e pi, that is the identity permutation, and that's equal to, therefore you get this. Okay, therefore, taking analogy from our experience of working on R2 and R3, we will interpret this as follows. Lambda determines the scaling factor of the unit n parallelepiped determined by En to the volume, n volume of the n parallelepiped n that is what you have, that is the volume of the n parallelepiped determined as x1, x2, xn equal to determinant of t, that is the scaling factor, n, and where t is equal to TEI equal to. So once again the same picture holds, but unfortunately we are not in a position to draw the picture, and we have already seen how it looks in the case of R2 and R3. So you have got a sort of unit n cube. I want to call it unit n cube. The volume, that unit n cube gets mapped into some parallelepiped. Once again, the remark holds that if these vectors are linearly dependent, then what is going to happen is that the determinant is 0. Determinant of t is 0. Okay, that means this n parallelepiped collapses into a lower dimensional parallel in n dimensional space R. Okay, so that is the interpretation that you have. So when they are linearly independent, you get a n parallelepiped, whose volume is not equal to 0. Okay, so that's the interpretation that you can give, geometric interpretation that you can give for this. So the scaling factor is completely determined by the basis, what you call alternating and linear form lambda. So that the purpose of this is actually this. This is the interpretation that you give for this basis vector. Okay, thank you very much, and we conclude here. So that also concludes the lecture series on determinants. I'll be coming back with another series of lectures on a different topic, most probably on Lebesgue measure and Lebesgue integration before soon. Thank you very much.